Here it is. So we have now not one vector, but three vectors, u1, u2, u3. And we given that this is the orthonormal system. How many people in this class remembers what the orthonormal system is from the first year? It's good. It's a good rate of memory performance. Basically, it's explained right here. Normal means that all the vectors are unitar, which is what we need when we discuss your directional derivatives. And ortho, this prefix ortho, means that they are pairwise perpendicular, and that is right here by the dot product like so. Right. So the example which I'd like to show you with the directional derivatives is this example. Look at this. Show that if you compute the sum of the squares of the directional derivatives with respect to these three vectors from the orthonormal system, so this time we're looking at one directional derivative, like in my previous example, but three together, three vectors, three directional derivatives in pairwise perpendicular directions. All of these symbols individually, they are numbers, right? They're not fruits. We discussed this yesterday. You can sum them up as squares. It will be another number. What I claim is, or what the example claim is, it will be the same if you take the sum of the squares of the Cartesian derivatives, x, y, z derivatives, which is, in another language, the magnitude of the gradient, right? Because the gradient is something which consists of these pieces as components. That's the coordinates of my gradient. So this is it. So we need to equate these three directional derivatives to the Cartesian ones. Here's just a reminder what the gradient is. Nabla f is that's the vector with these components. Right. So I'm going to use this result. The only result we know, the only result we need to know about the directional derivatives, how to compute them via the dot product. So this is the result. This is this result used 3 times for the u1 direction. You see, rate of change in u1 direction, dot product of these two. In u2 direction, again, rate of change of vector in u2 direction, and in u3 direction. I just use the same result 3 times, 1, 2, 3, for different vectors. Right. After you know this, the finish of the solution actually, it just involves one result from the first year. Some of you may remember that. Some of you may not remember that. It's certainly in the tutorial book for the first year. 100%. I'll just open the result and I'll ask you how many people remembers the number of that question in the tutorial book. That's why your performance probably will fail you, right? To remember the performance. Well, at least maybe you recognize it without the number. Look at this. So I'll call this lemma. I just frame it as a lemma. So look what it says. The result says this: if you have any vector in R3, any vector, no matter which one, it has not. Some already remembers the result just for these two things. So the result itself has nothing to do with the gradients or calculus. It's just a vector result about the vectors. So if you have any vector from R3, then the result says this: the magnitude of this vector, which we know how to compute it, right? It's sum of the squares of the components. But you also can compute it like this value. You take dot product of this vector with these 3 elements of your orthonormal system. You end up with numbers. You square them, sum them, and that's the magnitude square. How many people remember this result from the first year? That's good. That's good. Do you remember the proof of that result? You don't. It's a very short and very beautiful proof, actually. We can swap. We can just. No, it's right. It's so fine. If you remember something, it's good. I'll show you my version. It may click with yours, or maybe you have something else. It's all. I mean, probably you can come up with a few different ways to prove it. So look at the proof of the lemma. If you believe in this lemma, if you just reference this result from the first year, and for instance, if you persistent enough and you find this result in the yellow book, you find a number, then you can say, by that number, I can just finish the question straight away. Because look at this. If I use this lemma for the gradient vector, if you just replace the gradient vector here on the left-hand side, this right-hand side will be this value, right? Dot product, and dot product. So this lemma is this connecting element which links this value to this value. And if you remember the number from the yellow book unfortunately doesn't have an index, I think, does it? So it's harder to find this question, but with some effort, probably you can. If you reference that, that will be quite a complete solution. But here's the proof. The proof is nice. The main claim which we need to remember from the first year is that orthonormal system, and U1, U2, U3, it's my orthonormal system. It's the one which also a basis. It was another question in the yellow book. There was such a question, I clearly remember that, though I don't remember the number. This is a basis. And because it is a basis, every vector can be represented as a linear combination of the elements of this basis. Oh, no, what did you do? Sorry. Hence, X is a linear combination of these vectors with some maybe unknown, I mean, we don't know them, with some numbers. In general, when you try to figure out those numbers, if you have any basis, and you did this quite a few times in the first year, probably you're now bored to death, when you were bored to death with these sort of things, you have to use the Gaussian elimination, all of these systems, you need to solve them to find this x1, x2, and x3. But when you look at the orthonormal system, finding such representation, finding these numbers x1, x2, x3, is just, you can do it by direct formula. That's how you do it. Look at this. Furthermore, actually two things I have to show you now. On one hand, if you compute the magnitude of your vector, this vector, which is given by this formula, magnitude is a dot product of x with itself. If you replace x with this right-hand side, that's a replacement. And if you do the expansion with the dot products, you can do regular expansions as with the normal product. When you do the expansions, you can cancel lots of things. Actually, lots of things will be zeros. Every time you dot product u vector in the left factor with the u vector in the right factor, every time the indices are not identical, the product will be zero. That's the orthogonality of the system. And all those terms, they will disappear. All the terms where you product a u vector on the left-hand side with the same vector, with the same u vector on the right-hand side, only those products will stay, and those products, so only those products stay. When you dot product u on one side with the same u on the in the second factor, numerical coefficients obviously will be squared in that case. All the rest will just disappear. It's a step which is hidden by these dots. And then, because you also have this, because the system is also normal, these dot products, they are just the magnitudes, the lengths of your vectors, which are 1 all the time, and you end up with well-known Cartesian expression for the magnitude of the vector. Actually, that's a wrong comment. Forget about the Cartesian. It's just these are not the components of the vector. X1, X2, they are not components like in the vector. They are the coefficients in this representation. So even though it looks like the Cartesian formula, it's not. These are the sum of these coefficients with respect to the orthonormal system. It's one thing that I note, and the second thing I note, on the other hand, if you take the dot product of x with u1, again, if you use this piece on the right-hand side in this representation, if you sub it in, you will have something like this. And when you do the expansion again, here, when you do the expansion, every time you dot product u with u1 on this side, it will be 0 as long as you're not taking u1 in the first factor. But when you're taking u1 on the left-hand side, it will be 1. For the same reason it is 1 here. That's why it is x1. And that's the beauty of dealing with the orthonormal systems. in general, when you have a basis which is not orthonormal, finding these coefficients, it's not an easy task. I mean, it's a very, very algorithmic task, but still it's a lengthy task with the Gaussian elimination and solving of system of linear equations. In case you're looking at the orthonormal system, here, direct formula. Dot product delivers first x1. Similar dot product, and I'm hiding the same piece by dots here, delivers x2. And the final dot product delivers x3. And that's the finish of the lemma, because here, on one hand, the magnitude of your x is sum of the squares of x1, x2, x3. On the other hand, x1 and x2 and x3 individually, they're given by these dot products. So that's why you have this right-hand side in here. That's the proof of this lemma, which was framed as a question in the first year. This is just a quick refreshment what happens with that. And now if you use this lemma back to my original question, if you use this lemma with my original question, this identity, that will finish the proof of that identity.